Okay, the final installment in this fluid mechanics adventure that I hope you've enjoyed as much as I have. Okay, so we finished with a discussion on the force of lift. So first of all, here is the equation that we derived a couple of lectures ago that describes the force of lift for what we had was a small surface, and we calculated the integrated contributions of both the pressure and the wall shear on that small surface. If you recall, we looked at a small little element of surface like this, and we had the angle between the horizontal and the pressure. This was the pressure, this was theta, and we calculated the contributions of the pressure and the shear to both drag and lift for the case where the velocity was parallel to the x-axis. So we sort of simplified the problem a little bit to be able to get this result. But we also realized that this is okay. It gives us some idea of what's going on. It explains some things to us, but it really is not very helpful in practice, because in practice we don't really know the distributions of pressure and wall shear. In general, unless we do some CFD, unless we do a numerical simulation, we can't really know the pressure and wall shear stress at every point. So for that reason, we work with the coefficient of lift, which is the lift force basically non-dimensionalized by the dynamic pressure and the area. 1/2 rho v squared times the area. And then the lift, the coefficient has to be obtained from experiments or a numerical simulation. And this is how we need to operate in practice. The most important effect on the coefficient of lift in general is going to be the shape of the object. So one of the first sort of theoretical results that we have explaining lift is due to Lord Rayleigh. Lord Rayleigh in 1878, and I have here, I think, another slide for this, so if everybody's finished writing, I'll clear this one up. Lord Rayleigh in 1878 studied the flow around the cylinder, and he observed that if the flow, let me see if I have this picture yet, if the flow was exposed to a parallel uniform flow in ideal flow, so we're neglecting any effect of friction. So imagine this is an inviscid flow. If you have inviscid flow around the cylinder, then there is no separation, there is no friction, there is no drag. So this is what's known as the paradox of D'Alembert. We have no drag force in inviscid flow. No force whatsoever. But he considered that if you, still in the inviscid ideal flow theory, if you add a circulatory flow motion to this hypothetical situation, which is superposed to the parallel flow, then you get a force. This is what he observed. And here's the situation. So inviscid ideal flow, no viscosity. Then we have here, in the case of just a parallel flow around the cylinder, we have no force whatsoever on the cylinder. No drag, no lift, nothing. If you add a circulatory flow superposed to the parallel flow that we have right here, so you have A plus B, you have these two flows, what happens is that the velocity at the top, so if you have, let's call this point A at the top and point B at the bottom, and in point A, what you have is that the velocities are in the same direction, the circulatory motion and the parallel flow are both in the same direction, therefore there's an acceleration of the total velocity there is larger. In point B, we have the parallel flow going from left to right and the circulatory motion going in the opposite direction, and so there's a reduced velocity in point B. So this is the combined effect. In point A, we have a greater velocity, and in point B, we have a reduced velocity compared to just parallel motion. This is still ideal flow, okay? Now, this result was used to explain the so-called Magnus effect. The effect here can be very easily explained using Bernoulli's equation, because if we have a greater velocity here and everything else is ignored, if we ignore the effects of elevation, which is reasonable when the objects here are not very large, and we ignore the effects of friction, so it's still ideal flow, then over here, if we have a greater speed in A than B, so velocity in A is greater than velocity in B, and therefore the pressure in A is smaller than pressure in B simply by Bernoulli's equation, and we have a net force in the perpendicular direction to the flow. You have a question, Tim?
Does S the stagnation point of its distance to be decreased as angular velocity increases?
The stagnation point, yes, you're right, S is the stagnation point. Because of the added effect of the circulation, the stagnation point in the front has moved to a little bit lower point. The one in the back has also moved. They both are closer to point B, and if you have a bigger and bigger circulation, these 2 points are closer and closer to B.
Okay, correct.
So we have a net force in the direction perpendicular to the flow. Okay, this net force was this effect here. This result was used to explain what was at the time known as the Magnus effect. The result due to Lord Rayleigh was used to explain an effect that was known at the time, Magnus effect. It was known by the artillerists. 19th century artillerists knew that if you had spin on the shot, then it would change its properties of trajectory. Because of course, if this force is vertically upwards, it is going to reduce the effect of gravity and increase the range of the shots. And if the force is vertically downwards, it's like an increased gravity and it decreases the range. And this is the same effect as well that we can observe in sports, in many sports, when you add a spin to the ball. And this is an effect that is also discussed in quite some detail in some of the reading that I've shared with you on the Blackboard site. The effect of the spin, because of course in the case of, say, the baseball, there's a roughness, right? There's roughness because of the seams. That roughness causes the air around the ball to be more easily dragged with it. So when the ball spins, the air spins with it, and so there's a circulation on the air added to the translation velocity, produces this effect. A force which can point, depending on the spin, can point upwards or downwards or sideways and cause um, change in the trajectory, an increase in range, a reduced range, or a bending, either one. Yes? This effect is described purely by inviscid theory, yes. No, in this case, we are hypothesizing the existence of a circulatory motion that's there somehow. In the real case, the circulatory motion is produced by the spin of the ball. But in the ideal case, we can get to the same result, but we have to sort of impose from outside and say the fluid is rotating by some means that we don't know. And the fluid is here in the same way as we don't know why this thing is moving left or right, right? You just say, if we have the superposition of a parallel flow plus a circulation flow, the result would be a force.
The velocity is it's the velocity of the fluid, not the object.
In this case, it's the velocity of the fluid at precisely this location, okay? Right? Actually, no, the angular velocity, right?
But it's not like the object.
In the real case, it would be the object, but in this case, it's an ideal flow where we're just thinking that the external fluid somehow has a rotation, and the object in this case, since it's inviscid, we don't impose the no-slip boundary condition, so the circulatory motion is present in the fluid without the effect of the solid in the ideal case. Yeah. But the interesting thing is that even within the context of ideal flow, we can explain the presence of a lift force. And this is good because it means that we can use some results from ideal flow, which are easy to obtain, to describe some of the things that we observed experimentally in terms of generation of forces in objects. Now, this is very important, which is that, we see a symmetric object, a cylinder or ball, which can produce, well, a symmetric object, of course, produces no lift in general. But when we have a circulatory flow added to it, then we observe a force of lift. And that's the interesting result, and it's also very important that we can explain that result in the context of ideal fluids. This effect, as I said, is used in many sports. When you add spin to the ball, in that case, the friction of the ball creates a circulatory motion, but it was also used to create a type of wind-driven vessel by the engineer Anton Flettner. He created what's called the Flettner rotor for a ship in which you had vertical cylinders that were rotating. These rotating vertical cylinders, you see them here on this old picture of a ship, okay? Basically, the rotating cylinders acted like sails. They were able to generate a force by the superposition of the horizontal movement and the rotations. And I have a couple of other pictures. Here's a modern version of the Flettner rotor. Jacques Cousteau had one. Here is another one.
Do they have rudders?
Yeah, you still have a rudder.
But it's just
It's exactly the same as a sail. It produces a force which is perpendicular, or it has a different direction.
Oh, okay, that's that force.
And the force helps to propel the boat, but of course if you want to turn, you need to use your rudder. Oh no, because if this is a cylinder, okay, so if I look from the top, if I look this boat from the top, I have these two cylinders which are rotating. And suppose that there is a flow direction in this, so each cylinder will have a flow around it, and then the rotation adds and makes this faster around this side and slower around the other side, so that you get the effect of a force, a total force in that direction.
So this force isn't at lift at all.
Well, in this case, the lift is sideways.
Okay. It's not perpendicular. I thought it was a lift is perpendicular to the flow.
Yeah, but in this case, we're looking from the top, and it's perpendicular in that sense, right? Yeah. Now, this was actually very successful in terms of engineering and very successful in terms of the physics. The only reason that this failed was purely economical, because you had to have actually quite a high velocity of rotation on these cylinders. And to allow this mechanically, you needed to have these very sophisticated ball bearings, very complicated mechanical systems that require specialist maintenance. And it meant that, maintaining the sails of a sailboat is a lot easier than maintaining all of these complicated mechanical bits and pieces that were, associated to this ship. So the only reason it failed actually was economical reasons. But in terms of innovation, it's a pretty clever design. So this explains to you how there's this idea that circulation added to a parallel flow can explain the force of lift. All right? So let's discuss this circulation a little bit more. So circulation is a characteristic of a flow field, and there's one can spend a lot of more time talking about this circulation. But let's just state that it gives a measure of the rotation of the flow. How does it measure it? It's a measure of the rotation of fluid particles that are inside a region which is enclosed by a closed curve. So let me draw a picture in a moment. Enclosed by a closed curve is a little bit, let's try something a little bit better sounding, a little less awkward in terms of the English. So bounded, how's that? So suppose you have some velocity field. This is just a velocity field in 2D, and I'm going to draw just a closed curve. And this closed curve, let's call it L. And then what we can what we use to define the circulation is the path integral. We use the Greek letter gamma. The path integral around this closed curve of the velocity sub L, which is the tangential component of the velocity dl. So this is going to be an integral around L, and VL is the velocity at any point that is tangent. Oh, let me try again. To the curve, and we go around it to make this path integral. So VL is the component of velocity tangent to dl. Okay, so we have a definition, a precise definition of circulation in the flow now, and there's of course a lot of results in aerodynamics around this. I just want to give you the tip of the iceberg and some little samples of what we have available for aerodynamic theory. There's a very big player in this whole history, which is Mr. Zhukovsky, Russian, of course. That's a K. And he showed that a cylindrical body of any shape, any cross-section, moving at velocity v in a field with circulation gamma would experience a lift force with velocity v and circulation gamma will experience a lift force L equal to rho v gamma. But that is per unit length, so it's not the total per unit length of the object, right? So if it's a cylinder, this is per unit length in that direction. Okay, so this is a very interesting result that we can use to apply ideal flow to some explanations of lift. So what does this imply for an airfoil? So we study then what's called two-dimensional wing theory, two-dimensional in the sense that we're just looking at a cross-section of a wing that is assumed infinite on both sides, just to be able to use two-dimensional theory. And yes? Circular body, what do I mean by that? I mean cylindrical. So let me just, actually that's more precise, let's say cylindrical. Sorry about that. Cylindrical of any shape. So like, of course, a cylinder, but it could be any shape. And if there's a circulation around it, plus a velocity v, this is circulation gamma, velocity v, then there will be a lift force, and lift force is going to be given by this expression, rho v gamma. And of course, he demonstrated this, he obtained this result using mathematics.
So, is that a vector?
No, gamma is the result of this integral. It's a line integral. So around any curve you measure the circulation inside that area of all the fluid particles by doing this combination. I'm afraid I can't really spend great time to explain where this comes from. I just want to give you a little sort of inkling of what this whole theory is about. You can actually have a whole course on aerodynamic theory that would go into a lot of detail about these things. We're just trying to give you an idea in one class. So let's see what this implies for airfoils. So for an airfoil, inviscid flow, so what we want to do is to be able to use the inviscid flow theory to get some results for the case of an airfoil. If you have, in the case of inviscid flow theory in 2D as well, we're considering just a cross-section of an infinite wing. If you have a symmetric airfoil, at zero angle of attack, then there is no lift. It's the same case as a cylinder. The flow just goes around. We have one stagnation point in the front, one stagnation point at the back. The streamlines are completely symmetric, and there's no force whatsoever. Because this is inviscid, there's no drag either. There's just no force. That is the case for ideal flows. Now, still in ideal flows, if we have, again, the same symmetric airfoil, but with an angle of attack greater than zero, ideal flow theory would result in no lift, again, but you would also have some reverse flow in the back. as the fluid adapts to this angle of attack. This reverse flow in the trailing edge is unphysical. We know from observation that whenever we have a sharp edge, separation has to occur there. Remember when we were talking about the flow around a sharp plate, and we said the flow has to separate at the sharp edge when you have a flat plate perpendicular to the fluid, to the flow. And that applies as well in viscid theory. So really, separation has to occur on the trailing edge. And so this is not realistic, and the way to reconcile this problem is to impose a circulation in the flow, the same as we were discussing in the beginning for the circulant cylinder. We hypothesize the presence of a circulatory motion in the fluid such that the circulatory motion is able to increase the velocity at the top, decrease the velocity at the bottom, so that the stagnation point moves to the trailing edge in this ideal case. So we know that in real fluids, separation must occur at the trailing edge. And so the theory is made to agree with the physically observed phenomenon by hypothesizing a circulation around the foil, the airfoil. So. And this circulation moves the stagnation point to the sharp trailing edge. This is represented in the sketch here by this situation. We have here the unphysical result from ideal flow of a symmetric airfoil traveling in a greater than zero angle of attack with reverse flow in the back. We add this circulation, and the result is separation at the trailing edge, which is the physically observed type of flow. The contradiction is basically stems from the fact that we're trying to use ideal flow theory to explain something that is, real flow. But it is reconciled through the use of this circulatory motion.
Oh, it's to say, I think it should be B plus circulation, not A plus circulation.
Maybe this one. Yeah, I've stolen these pictures from who knows where, and so this could be the A. So A plus circulation equals C. Oh, A? Yeah. That's a true typo from the whatever. So it's a true typo. Yes. But from yes, it's B plus the circulation equals C. The next add-on to this is, well, we said that the theory is made to agree to the physically observed phenomena by adding the circulation, and then we have what is called, what is it? The Cotta condition. So this is the Cotta condition. The fact that we have a circulation around an airfoil such that its pressure, such that its presence moves the stagnation point. To the trailing edge. This is called the Cotta condition. We must have separation at the trailing edge, there is in fact a slip layer in the back, which is called a vortex sheet, because basically the flow here has different velocity than the flow here, and so there's like a slip velocity there in that layer in just the trailing edge. This actually introduces vorticity, rotation to the flow, and contributes to several things that we will discuss now. So the advantage of trying, to force things a little bit here to use ideal flow to explain a real situation, which is the generation of lift, is that we can now use some of the results. For example, we just had a result from Joukowsky about the lift when you have a velocity and circulation, right? We had this expression. So what happens when we use ideal flow, ideal theory to calculate the magnitude of the circulation required? So ideal flow theory used to calculate the circulation, the amount or the magnitude of circulation required. To produce this, the separation just at the trailing edge, gives the following result. We can't prove it in this class with a limited amount that we've studied potential flow, ideal flow theory, and so on, but it gives, for a symmetric airfoil, gamma equals pi c v alpha, where c is the chord, v is the velocity, of course, pi is the number pi that we all know, and alpha is the angle of attack. So one can actually rigorously get this result. Now, if we add to this the result by Joukowsky, which is that the lift force per unit length of wing or cylinder is equal to rho v gamma, and we combine this, we get that the lift force is equal to, so now we put the exact amount of circulation that is required to have the separation point at the trailing edge, and we get rho v squared pi c L. I multiplied both sides of the equation by L, the length of the wing, even though we're using infinite wing theory, this is per unit length, so we're just basically ignoring any possible end effects at the moment. So with the definition of coefficient of lift, which is lift divided by 1/2 rho v squared s, and note that the surface for lift is the planform surface, which is the length of the wing times the chord. So S equals L times C. Then we get that CL, according to ideal flow, is found precisely as 2 pi alpha, a direct linear relationship with angle of attack. And this is actually pretty close to what one can observe, except that at a given, that this is only applies for small enough alpha that there's no separation, because then if there's separation, then we definitely cannot use ideal flow theory even with any of the tools that we want to apply. So these are the theoretical lift equations for an airfoil. And they have turned out to be quite useful. They were the first result, the results available from theory that were of any use whatsoever to study flight. But of course it breaks down once you have separation, or what we call stall, then this no longer applies. So finally, let's see what happens. This is all assuming there are no end effects. So even though I've used here that there's a planform area, so there's a finite length or a given length, I've assumed that all of this theory is actually for two-dimensional airfoils, therefore we have no end effects at all. But if we introduce a finite wing, finite length of wing, then we have those effects. And what really happens is that at the ends, you observe these trailing vortices or wingtip vortices. Now we were talking about this circulation that is present in around the airfoil, right? So if I look at this from the side, if I look at the airfoil from the side, if I look at the airfoil from the side, there's a circulation around it, right? That's if I look at a cross section. Now if I look at the finite wing, you can imagine that that is actually called the bound vortex. And you can imagine that that bound vortex, once you get to the ends, it actually turns around like a horseshoe, and you have the vortex going all the way back to the, in the wake, and you have this effect of the wingtip vortices. Or another way to explain this, without using the bound vortex, is that there is a higher pressure at the bottom of the wing and a lower pressure at the top of the wing. Therefore, in the edge, in the wingtips, that higher pressure air must, tries to go over and generates this circulatory motion here in the edges. These trailing vortices have the effect of reducing lift with respect to the ideal two-dimensional theory, and they also increase drag. This increased drag is called the induced drag or lift-induced drag. Just the generation of lift have to be associated with some drag, which is present in finite length wings. And you can imagine that there is a different amount of this effect depending on the aspect ratio of the wing. If the wing is really short and stout, then you will have a lot more end effects than if you have a long wing, like in sailplanes or soaring beds. You have very long wings and you have reduced effect of the wingtip vortices. So the aspect ratio of the wing has influence in this effect. And also this effect can be reduced by adding winglets. These guys over here. I have a picture. Oh, I have pictures of trailing vortices. Let me show you the winglet. Oh, look at that. Yeah, I forgot. I forgot I had all these good pictures of. These are actual demonstration observations of the wingtip vortices. They can be very strong. This is a duster, and so you can see a duster plane, and you can see very strong effects of the wingtip vortices. Here, the wingtip vortices are visualized by the cloud cover. The clouds are visualizing there. These are actually visualized by the smoke coming from these. They could be flares, right? Yeah. And this is pretty good, actually, because you have very strong vortices coming from the edge of the flaps here. The flaps extended, and those flaps generate also some trailing vortices. And another one. So what happens here is the vortices, of course. Remember when we talked about Bernoulli's equation perpendicular to the streamlines, and we had a rotating flow. We had a result that for tornadoes explained why there's a reduced pressure in the eye of the storm. The same thing happens here. You have a vorticity generation. You have a vortex here coming from the wingtips, and so there's reduced pressure at the core of that vortex, and with giving environmental conditions that can produce condensation, and the condensation visualizes the presence of those vortices. And that's what you see there.
Can you prevent that by cleaning up the edge of the wing?
Yes, we can improve on that by doing the using the winglets. I'll have a picture in a moment. But look at this one. This is really, really cool because you have actually this plane is breaking the speed of sound. And so there's the condensation behind the shock wave, you can see here, and the condensation from the vortices on the wingtips. This is the coolest one. And here are the winglets, which are there precisely to reduce the effect of the wingtip vortices. So anyway, that's the end of the material. Thank you all for your attention and your patience at some points of the course, and I hope that we've combined a good mix of things for your first introduction to fluids. And I'll see you on Wednesday for a review class and preparation, exam preparation class.